with that, it's my pleasure to introduce Paulo Lima-Filho from Texas A&M University, who will speak about currents, ordinary equivariant, cohomology, and regulators for real varieties.
Thank you. I hope my voice will survive to the end of my talk. It went bad starting last night. It's more than a pleasure to be here, as already stated before. But in trying to package my talk for today, so because of the title of the conference, I tried to put the right twist that I could perhaps appeal to more differential geometries in the audience. And also along the way, I will try to emphasize tangentially some aspects of Blaine's work that I don't think have been properly emphasized so far in the audience. So he did a lot of things with algebraic cycles. That's what I entered. I had applications also to interesting problems in homotopy theory as well, and in some sense also served some inspiration, or at least one of the first anthology as such, the development of Voevodsky approach to motivic homology. Although, so those things are by no means should not be neglected. So let me state the brutal goal, what it is, and I'm expecting that everything written here, part of it, will not be familiar to most of the audience in the way I'm writing it. But then, along the way, my goal is to try to explain some of the ingredients that appear here and try to put in historical context. Actually, I wish this had been the first talk in the morning because first of all, I would not be following Claire's act, and secondly, because some of these things would be somehow almost the background for my talk. But so the idea is that we have this notion of motivic homology as introduced by Voevodsky, and I'll try to do something, the differential geometric version of it that will give you only, let's say, basic singular cohomology, or in the equivariant sense, what's called ordinary equivariant cohomology. And then there are some realization maps from this motivic homology to Deligne cohomology. So, so I've also explained what Deligne cohomology is, but a version of it that it was introduced by dosSantos and myself a few years back for varieties, real varieties, and so you can think of them as holomorphic manifolds with an anti-holomorphic evolution if you're not an algebraic geometer. All right, so I was here. So let me tell about some recent history first, because over the complex numbers, such a map, such a so-called regulator maps, their existence was first shown by Spencer Bloch in some very...
Definitions.
I will.
You want us first before the definitions?
Yes. I now go back to it. So all I'm saying here is that, I'll give some more historical motivation or older history. But basically the idea is that the proofs of such thing always use either very abstract and completely non-constructive ways, or they use an isomorphism between what people call Bloch Chow groups and motivic homology. And that per se is already pretty difficult to prove, and somehow uses what's very similar to the arguments that Blaine used to show some duality between the Lawson and morphic homology, Friedlander. But so what you're going to do is something also that is doesn't look very clear here. But what I'm going to do is give a map between two complexes that I'll introduce all of them. One complex is complex of sheaves that gives motivic homology, and another one that gives you Deligne homology. So now let me start with the following. Basically, the whole idea, what I'm going to do for half of the talk, is to give a very complicated way, to a certain degree, of defining singular cohomology. So for example, let me give an example. Suppose you want to suppose you have an integer p, and you pick an integer, say n lesser than p, and you want to compute the singular cohomology of x with coefficients in z. You can think about this as reduced cohomology if you have a trivial base point. and then maybe you want to use suspension theorem, and then now you have that this is the pth cohomology of the n minus p suspension of x plus. So I'm just complicating things a little bit more. But then here, you know that suppose x is a nice complex CW complex. You can think about this as homotopic classes of map from this to a certain space, which is an Eilenberg-McLean space. Right, so there is such a space that guarantees this definition. But then I want to complicate it a bit more. Using adjunction here, you know that this is homotopic class of maps from this to now I will take the function, the base, or the function space, since I have this, from this into the Eilenberg-McLean space. But so, again, this is just a little adjunction that I make here. But I want to complicate more, and I'll think about this as the n minus p homotopic group of this space of functions. Yes, there you go. So now, what we're going to do next is first of all tell you a suitable way of constructing the space that will be able to bridge two worlds. There's some sort of differential geometric approach and the completely algebraic geometric approach of Voevodsky, and tell how to transform this and this homotopic group into more sheaf theoretic definition. Okay, so let's start with the category of oriented and real analytic manifolds and analytic maps, and let's think about contravariant functors from that to abelian groups. Let's call that pre-sheaves, abelian pre-sheaves on analytic manifolds. And for example, examples of those, a manifold itself defines a pre-sheaf by taking all analytic maps from U to V and take the free abelian group on that. Of course, that you can, if you start with a smooth manifold, you can also define a contravariant functor from this category to abelian groups just by taking the smooth maps. So ignore whatever analytic structure U has, it's still smooth. And so they give example of functors from the category of analytic manifolds to the category of pre-sheaves. And the first one can be thought of like a free pre-sheaf generated by the manifold V that you pick, the analytic manifold. So for another example, say smooth p-forms define a pre-sheaf, that seems it's manifold to the forms. You could take etc. And now define what a finite analytic correspondence is. So basically you can think about these, if I give you V and W manifolds, you can think about some sort of a current, a locally integral current in the product that projects on the first factor properly and has finite fibers. But I think Bob Hart convinced me that if you start with analytic, real analytic currents, right, that would be, I would get rid of all problems with slicing, intersecting that they needed if you try to do with more general currents. But I would still obtain sheaves that would give the desired result. So, I mean, of course, I'm not counting orientation here, but you can think about this. So, the finite analytic correspondences we think about as a current in the product, which is closed for the moment. The restriction, the projection here is proper on the support of the current, and the fibers are finite, and this forms an abelian group, that's the notation of that. But I want this to be thought essentially as a map from the base to, say, zero cycles or zero currents. On the other space, you project down. So here's an example of the slicing process. So examples, of course, that and they're relevant for what I'm talking. If you have any real analytic map, the graph is an example of such thing. But if you have also, say, if you have two real varieties, X and Y, so you can take, those are objects are described by real equations, and so it schemes over the real numbers, called that way. And this, I look at the complex solutions of that, of course, that with analytic topology becomes a holomorphic manifold with an anti-holomorphic action of the Galois group of C over R, right? It's a complex conjugation, so the solutions come in pairs, of complex conjugate pairs. So then, but anyway, so if you have such a closed subvariety of the product that is finite in the algebraic geometric sense over X, and you look at now the analytic subvariety associated to that, it also represents an element that lives in the space of currents that I call finite analytic correspondences. Of course, that these spaces are always oriented universally if you make one choice of square root of -1. And so, of course, you can extend this type of example for more general algebraic cycles. So I'll leave to you how to define that. And now we're going to extend this a little bit to include manifolds with corners. And you can just try to extend the notion of finite analytic correspondence to this setting. So I will skip details on that, but you can extend that to manifolds with corners. And now we have a composition pairing between finite correspondences that actually it's not so. So suppose you have a correspondence here between X and Y. So this is the usual. So I have here Y plus Z, and then here you have X plus Z. The point is that if I have a correspondence here, I have another one here, then I can take here, on top of this, I take gamma cross Z, I have a correspondence here, I take here X cross W, and then because of all the definitions we put in place, these two currents that live in this space, they intersect. So you can intersect them, so fine. And then the support of this, the restriction of this map to the support is still proper, and you push down here. And so you can define that intersection. So if you call it the pi projection 1, 3, you define pi 1, 3 push forward as current, and that will be the product. Well, if I call this correct, something like that. And that all works, right? And so we have the associative pairing. And an example, if the correspondence are just the graphs of function, this is precisely the graph of the composition of the function. So now we can think of this as a category. I actually, for those who know it, I'm just paralleling very closely. That's not the verb. I'm just going very parallel to Voevodsky construction of motivic homology, but just in a very differential geometric sense. And you can think of, you can create a new category where the objects are still the same analytic manifolds, but now morphisms are those correspondences, those maps. And the example I gave before, I can always send the manifold to itself and send an analytic map to the current defined by its graph, and I have an embedding of these two categories, which is faithful. So I can enlarge manifolds to include those currents, the analytic manifolds. So now let's take a little digression to see why in the world we want to introduce those currents and those things that are sliceable. I'll explain better what that means soon. There's this theorem of Ombre, and I think in many ways serves an inspiration for the subsequent definition of Lawson homology. But and I put manifold here, but this could be any absolute neighborhood retract in Rn. So if you give this the integral k currents the Fresnel topology, then the J homotopy groups of this group of k currents, if you think about this, think about a sphere, a j-dimensional sphere, parametrizing a family of k-dimensional cycles. You have the total family dimension j plus k. You can make sense of that up to homotopy, and that gives you a homology class J plus K. So Almgren's theorem say that this is an isomorphism. And so let's take an example of that. For example, if you start with a sphere, SP, right, so the same P that appears here, then and you take 0 cycles, so then if you put K equal to 0, then the J homotopic group of I0 is Hj. So therefore, if you play a little bit with this, you see that this space is connected, and modding out by the cycles of the base point. And then, because of this theorem, we see this space has only one non-trivial homotopic group. This is the the p homotopic group. Because of this theorem. This is just the homology of the sphere, the homotopic groups of this. So this becomes the model for the Eilenberg-MacLane space KZP. And if you are very picky about this, I mean, I'm taking the approach that homotopy theories is always retopologized thing by the compactly generic topology. It doesn't matter. It's a model for that. And so now I'm going to use this as a model for this space here, and in particular, for any complex W complex, we have that the nth dimensional cohomology of X can be defined as the P minus N homotopic group, just like this, of the function space of X into this model for the Eilenberg-MacLane space. Right? So this is the approach that I took while explaining what's here on the board. So now I'm going to proceed and try to go back to what I was explaining before and try to realize this homotopy group and this function space in the sheaf theoretic manner. Right? And so I guess as a result of the work of Voevodsky, a lot of homotopy theorists and hardcore folks in that direction, they, for example, Daniel Duggar and Isaacson basically show the way of developing universal forms of approaching cohomology theories on the site, and then you model whatever topology you put there, and you get several different ways of seeing the usual homotopy category in the same manner that you see the A1 homotopy category of Voevodsky. But so let's try to mimic that a little bit. First of all, I mean, this is for the geometric measure theorists, the way these finite correspondences were defined, their occurrence in the product of V and W, precisely nicely, and that goes back to the work of Bob Hart, that guarantees that these slices always exist for all x's, and not only that, we can then obtain out of such a finite correspondence a map from the base space to 0 cycles on the fibers. So that's a continuous map. So you have this visualization map, and that's how this should be thought in some ways. This map from V into 0 cycles in W. Not all maps are of this form, but these are good enough to capture the homotopy type of all such maps. So I think that's the philosophy that appears here. Now, everything I said here, you could translate in the context where you have manifold interactions here of a finite group, say via analytic diffeomorphism. And so we can, and for a pair of G manifolds, the finite correspondences then will be a G space under sort of the diagonal action of the group in both, if you do the right sense. And then, but from now on, I'll go to the simple case where G is just take a log group C over R. So it's Z mod 2, isomorphic to that. And now we're going to go, and this is essentially Voevodsky definition of what a pre-sheaf transfer is, except that they have these 2 other names that I'm saying that is a contravariant function from the category of analytic correspondences to abelian groups. We call it the equivariant analytic pre-sheaf transfer, GPST, whatever. All that. And again, an example is the pre-sheaf represented by the manifold V itself. So you have here V, and you look at the correspondences. So this is a canonical type of Ioneda embedding that sends the category of manifolds now inside the category of GPSTs. So that's the analytic presheaf represented by V. And now let's associate to that, to any such presheaf, we're going to associate a complex of presheaves. And it's simply by considering these dark triangles are the usual topological, compact topological simplices, and you have you make the group act trivially in those, so there's no group action here, and that's a cosimplicial object in G manifold, so it has all these relations. And if you have a presheaf F, then you define this simplices of F, if you want to call it that way, by always crossing U with delta n and apply F to it. So now, because the presheaf is a contravariant, then this becomes now a simplicial object in the category of analytic presheafs with transfer, and associated to this any simplicial object, you have this chain complex, right, by taking the alternating sum of the faces. But now I want to see that as a cochain complex by making everything negative, and so it's all graded negatively but going up, so from minus n to minus n plus 1, etc. And I create this complex of presheafs with transfer. These are nice because if you look at the cohomology sheaves associated to that, they have what they call homotopy invariant cohomology. And that also will be important in the proof of a statement that comes soon. So now let's complicate things a little bit more. So now remember that the group is the Galois group of C over R. You have, I wanted to define the smash product of those things. So basically the idea is that in the presheaf level, we mod out by the submanifolds that would define the smash product of V with itself. There's a typo here, this X should be V. So it's a little mistake. But that's a way of defining the smash product of those objects. And now, there comes the main object that I introduced. This is the category of manifolds with an action of the Galois group, right? There's an action of the Z mod 2. And here we are taking C star, so it's C minus 0, taking this mesh with itself P times, and then I take this similar complex associated to that. So this is something that's graded negatively, and then I translate the complex P slots to the right. So this is a complex where the last non-trivial sheaf appears in dimension P, and everything goes down to minus infinity. So it's a complex of equivariant presheafs with transfer, and this will, there's one thing that I like to bring to the attention, is that if before passing to any quotients, right, C star you have here as 1, as it's invariant under the action of the Galois group, right, the unit circle, but then this is like the one-point compactification of the sign representation of the Galois group. And so this is an equivariant retraction over here, so equivariantly they are the same. So when you do this, and then you multiply times itself P times, so then you have S1 to the P times inside that. So when I mod out by this, I would be modding out by also the same terms that will give you then the sphere SP again. And I take the free abelian group on the sphere. I'm throwing things on the rug, but in the shift theoretical way, this is okay. There's no vibration issues I want to deal with here. But this then, I'm looking at free abelian group on the sphere of 0 cycles on the sphere SP, and I'll get the same the same model for the Allenberg-MacLane space. So in other words, this is still essentially, when I pick, you should think about when I apply one of the elements of this sheaf, I'm looking at maps from a simplex delta n in the space of functions from X to an Allenberg-MacLane space. You bring up the homotopy, that's what we're getting. So, and now I want to introduce very quickly the equivariant topological context that I want to And for those who are interested in complex case, ignore everything I'm going to say for the next 3 slides. But given a finite group, in this case we have just Z mod 2, you look at the representation ring of that, is Z plus Z, generated by the trivial representation and the sign representation. And back in the 80s, Peter Matey's school, they developed this notion of equivariant cohomology indexed by the representation ring of the group. I think that it was Graham Siegel, probably in the ICM of 1970, that said that equivariant cohomology theories should be graded by such things. But, and then there's a theory that says that for every fixed representation, I can find these cohomology functors, and they all form a generalized equivariant cohomology theory. And why the alpha? Well, there's the suspension axiom that should hold, where the alpha cohomology is very similar to this isomorphism that we have over here. Is isomorphic to the suspension by the one-point compactification representation. So this is, and there is a unique theory that satisfies axioms once you have the appropriate dimension axiom. But now let's rewrite the cohomology groups that you get in the following sense. So the cohomology indexed by this representation, n minus p 1 plus p is sigma. So it has p copies of the non-trivial representation, n minus p of the trivial representation, and n is the total dimension. And so we use this indexing to denote this group. And I will tell you how to do that in a very, essentially you could do exactly this to define it, except that here a model for this would be the free abelian group on the sphere of the representation. And so that stems from the work of some of myself and Pedro dosSantos and Zhao Huni. They're all sitting here. And maybe I'm missing someone else amongst your students, Blaine, but many of us worked on that. So basically this is the theorem. One that starts the whole. I could do that in a different manner, but one way of, if you think about singular cohomology, for example, I'm saying that the nth single cohomology of X can be obtained as this, map in the derived category between the sheaf representation by X for any smooth manifold to this complex of sheaves shifted by n. So this is essentially what's written over here in the sheaf theoretic manner. Now, if the manifold is analytic itself, then it's simpler to write this. You just say that the nth cohomology group, which is P twist, is the hypercohomology of the manifold in the equivariant sense with respect to this complex of sheaves that we just introduced. And so I mentioned those names. I forgot to mention Haiboyan, a student of mine who also wrote this in a different manner, sheaf theoretically. So now I have this complex. I have this complex of currents, of sheaves that's constructed out of currents, that computes either single cohomology in the ordinary sense, or this Breton bigraded cohomology in the Z mod 2 sense. I could say a few more words about properties of that, but it's not the purpose here. So just there is a forgetful fun, and I'm going to make another realization of that since this cohomology theory to single cohomology, it's an n single cohomology group, you just forget about the equivariant structure, you just have the old sphere. But now is the invariance under the group in single cohomology under the simultaneous action of the group in Y, like Y is the G manifold, and here's to say that is the invariance or the anti-invariance if depending on whether P is even or odd. So another way of expressing that is you look at, and down it goes, start into the world of Deligne, you define by ZP this subgroup of C, which is isomorphic to Z, but it's a module over a log group, and you can look at singular cohomology integral coefficients, as having coefficients here, and take the simultaneous action. So that's a natural forgetful functor that I will realize it very soon in a different manner when you put ZP inside C. Now let's go to Deligne cohomology for real varieties. So this Breton cohomology by gradient has a lot of interesting properties. I will not go into it, but picks up a lot of interesting torsion invariance of the action. Now, for real varieties, we go to the construction of the Deligne cohomology in the same way as Deligne did, except that the Breton complex will replace the integers. So Deligne essentially had a complex that starts at dimension 0. This is the constants, going to holomorphic functions, going holomorphic one forms, and you go all the way up to holomorphic p minus 1 and you stop. So this is in the degree p, it stops right here. And so for complex manifolds, you use this complex of sheaves and you calculate the hypercohomology of the values in that complex. And that's the Deligne cohomology. And I will say a few more things about it in a minute. But now what you do is that you replace this, but not by this constant, you can think of this constant sheaf, but that complex of sheaves that they call BR. And so now some notation, now we're denoting the Theorem current on any G manifold using a lot group, but invariant under this action. So these are the invariant currents. And it's a complex of abelian sheaves on G manifolds as well. So now, if you interpret it the right way. So now, let's denote by omega p this form. This is again a form that is invariant under this action. And we have a map of complexes, that is to restrict with variety with the G action. We have a map of these complexes. And it's actually pretty simple. We're going to do that many times. So here now we have, you're always going to have your manifold. You're going to have a certain simplex here, let's say P minus J. Then you're going to have here, let's say C star to the P. And then so this maps to C star to the P. This maps to U, so it's pi 1. And the idea is that I have a current over here whose projection into this is proper. The restriction of the projection to this fact is proper. This map is also proper because I'm taking the compact simplex. And so if I pick a form here, and I have a current, I just take the pullback of the form, wedge the current, and push down to U. And so for all kinds of forms, I can do that. In particular, I do for the form that I call omega over here, and I get then an element in the distribution in the current, the run currents, so dimension J, degree J on U. And the proposition is that this map defines a morphism of complex of abelian sheaves on G manifolds. So you just verify that's not difficult. The form is closed, it helps. And so now we have a Hodge filtration, Hodge filtration, and we denote by the inclusion. And so now we define this Deligne complex. This is the cone of that complex I had, is the Hodge filtration. Under the maps I just introduced, the tau map is the map on currents I mentioned here. And this is the pth Deligne complex on smooth manifolds with coefficients in on. So defined over R. And so, and that's a definition of the Deligne cohomology for real varieties as a hypercohomology of that complex in a divine sense. So let me say a few words on the complex case, for example. So everything I said here could be done by forgetting the action of the group, and that would be the usual Deligne cohomology. One thing about, just relating to the talk of Claire a bit earlier today, for example, one of the examples of the Deligne cohomology, let's say 2p of x zp, Deligne. So actually, these are interesting groups. They actually surject on the Hodge classes 2p of x with z coefficients, and then the kernel is actually so-called the Griffiths intermediate Jacobian JP. And this thing has a cycloclass map for the Chow groups of p cycles mod rational equivalence. Such cycle map exists. from here to here. And the map from here to here is precisely the, I forgot what notation I used, but this is the cycle map that we're discussing. Right, and so, and now if this thing goes, the kernel of this cycle map, it's called the homologically trivial cycles, and this is the Abel-Jacobi map. And so the map that we are going to describe is a generalization of this map, right? Because in this is an example of the motivic homology, H2P X ZP motivic, which I'll introduce shortly. But essentially, what I'm doing is sort of a generalization, an explicit realization of a generalization of this map. Okay, so that appears in the talk. So, so again, some properties of this approach to the real case. The real case picks up much more torsion than so it really addresses torsion phenomena that the complex homology cannot pick up. But so this result I mentioned here comes from the same kind of exact sequence that comes from the fact that this is a hypercohomology of a cone, and and so the Deligne cohomology sits between the kernel of this map, which in this particular number, the case of the complex numbers is the Hodge classes, and this mod what comes before, which is in this case the Griffiths-Jacobian. So this exact sequence gives you that short exact sequence. Particular properties that, and then this you need to define in slightly modified form, but it has a natural bigraded ring structure. And the forgetful function is a map of bigraded rings. So forgetful meaning there is a natural map coming from the cone, from the Deligne cohomology to the usual equivariant cohomology, the generic cohomology, over the complex number that is just singular cohomology. And when p is equal to 1, then this complex Z1 is just O star shifted by -1. So in particular, H2 Z1 is the Picard group of this as a real variety. And the H11, when this is 1 and 1, this is just, if you have connected geometrically connected variety, it's just R star. This is proper, I'm taking them as proper varieties. Okay, so here's the picture of the cohomology of a point. So you see that I'm also defining it when the degrees are, p's are negative, we divide defining that as a Verdon cohomology. And so it's along this diagonal I have R star, 1, 1, and then this is just Z mod 2, but I'm writing as Z star plus or minus 1 over here. Particularly, there is an element over here, which is sort of -1, that when I multiply by itself, it gives you the additional generators that come over here. So I'm not going to go into that, but you could, for example, if you start with the number field, you could say, you could compute the cohomology of the spec of that tensor, seen with R, with the ring of integers, and then there will be a map from Milnor K-theory to this thing directly, for example. And so this part over here would pick up some non-trivial parts that the complex homology will not pick up. Okay, so but let me, now what's the algebraic geometric counterpart? That's motivic homology. That's going to go very quickly because I did this before with currents for differential geometers. Now for algebraic geometers, you just look at the free abelian group on the reducible subvarieties that finite and surjective over X. Let's suppose that X is connected for the moment. And if it's not connected, you define this in this form. So it's exactly the same picture I had here before, except that the varieties are now algebraic varieties. This could be defined over any field. It does not need to be real or complex, and this still makes sense. And for example, the graph is a finite correspondence. The correspondence for a point to Y is just 0 cycles on Y. And we have a composition pairing defined exactly in the same manner using intersection theory. And so you can define the same category of finite correspondences as we had before. That's what Voevodsky did. And his motivic complex now replaced this compact simplices by this algebraic simplices. You can think about this just the zero set of this equation over here of this polynomial. So this is just a canonical algebraic simplex. It still form a co-simplicial object in the category of varieties over the field. I put a C here, but it could be any field actually. And so this is the motivative group, like you can think about C star or in the same manner done here. And that's Voevodsky's definition of his motivic complex. So these are finite correspondences from this to this to the P, and then I mod out by those sort of diagonal, this hyperplane, these subspaces. And it's basically doing the smash product, as I mentioned before. And now I guess I hope that it's going to become clear how we're going to move. The idea is that you can define this.
The finite correspondences have image where?
I'm sorry?
The finite correspondences have image where? In Voevodsky's definition.
Oh, okay, so.
The finite correspondences from this algebraic simplex to.
Okay, so this notation can think about sort of a maps from this to this. So this is the algebraic group. The motivative.
Oh. Well, in the group.
Okay, so we see that as a writing, sorry. So this is GM is.
This theory again.
So essentially this is like taking C star times C star to the P times. So this is P times. You can think about this as GMP when you look at the complex values of that, if you think over this. And so, and here, I mean, I'm modding out those where the ith coordinate is 1. And so basically, I'm smashing this. I'm smashing this by the union of C star cross 1 cross C star.
The horizontal is U.
U and the simplex. U cross delta. So I have delta, say P minus J cross U cross, let's say C star to the P. Right, then I have a correspondence with an algebraic cycle over here. Right, and then an algebraic cycle over here that maps properly over this. Proper with finite. Basically, it's a finite map. It's proper with finite finite. And so this could be thought of, if you use some adjunction here, as a map from the simplex to the space of functions from U to the zero cycles on the sphere. Because I'm modding out by the.
Thank you.
Oh, that's this I here should be the I here.
Okay.
My apologies. So I'm taking all the time. So this I should be the same I here. This inclusion. Thanks. But we do the adjunctions and map from the simplex, and then you take the homotopic groups of that. But if you take the homotopic groups of the complex of the simplicial abelian groups, right? You get the homology of the complex of simplicial abelian groups is the homotopic one. So you know exactly what I'm talking about. So so then that's how it defines motivic homology, hyperhomology of X with coefficients in this complex of sheaves. And this heuristic topology, actually. Okay, so now I'm going to go through the properties very quickly, but certainly the very interesting property is that for one case a field. Yes.
So the main difference with the original
Well, Bloch, in some sense, Bloch's theory is more of a covariant functor, right? It's more like homology in some sense than cohomology. But what Bloch does, he defines a completely different, I think, complex. It's not defined as a hypercohomology. No, it's much more geometric. Bloch approaches. No, Bloch works only with those that intersect all the faces properly for all dimensions. Yes. So that's the major problem in trying to prove things, because you have to be invoking. I think the major flaw in this first version of the paper is that the moving lemmas are not in place, so that you guarantee that the desired properties would hold. And in this case, everything holds, just right definition. The difficulty showing how they are isomorphic for perfect field. That's where a lot of the moving, in some sense, lies hidden. Anyway, so in particular, this is what I said: 4H to P, ZP are the Chow groups of algebraic cycles. I'm going to mention T more rational equivalence. And so now I want to, the theorem, again, is a bit like the change of topology map that Clara mentioned in her talk, but we're going to find an explicit morphism of complex of sheaves that would be natural one X. And that would induce this regulator map from motivic to being something in the homology group. So, and let me do a sketch of the construction, because it started this differential form that appeared before. We define this P minus 1 form here. And then when you differentiate it, you can write it as a sum of this plus something else. Defines the difference of these two. And we're going to use these three differential forms together with this type of construction done here, plus some properties of that we clear soon. So the idea is that suppose you started with an element in the Voevodsky complex, right? So this gamma is actually a subvariety of U cross the simplex cross this. It's represented by that, right? Mod those who lie horizontally somewhere. And now we restrict that to the closed compact simplex, delta, that is contained inside here. So these are the solutions. You can think about this as the complex solutions of that equation, and these are the real solutions which are non-negative. Right? So one sits inside the other. But we can look at the complex points of this correspondence with analytic topology, see that as a current, which is also a finite current in the sense we said before, and you can restrict that on top of that simplex, and that restriction, because of all the functoriality properties that we described of the analytic correspondences, it will still make sense to define a current that lives exactly here, and it represents an element in this complex as I defined before. So just completely natural restriction to the topological simplex. Now the Deligne homology, so that would actually give you a map directly from motivic homology to Milnor homology. That's a definition, that's just on the notes. Or even if you do over the complex numbers, that will be a map from the motivic homology with the complex numbers to single homology with ZP coefficients. So the ZP actually are interesting, they come up if we integrate the form omega that I had before, the disease over Z is P time up here as a 2 pi. There are periods that are multiples of 2 pi I to the P that appear there. So that's all very natural. So now we defined this map before from this complex, the singular homology, say, the currents, the round currents. Now, and the other two that we define are essentially the same as this. Remember, I had this yoga of pulling back a form from C star to the P, and then wedging with the current and pushing it down. So I do that for these two other forms that we introduced before. And so they satisfy this identity of the rank current. Once you do that, and of course that the forms that you pick, they vanish whenever one of the factors is equal to 1, right? The Z over Z, I restrict to that. Therefore, those currents descend to the quotient that allows you to define motivic homology. And so now we can define a map from this. So this is the motivic complex, and pick a correspondence in the sense of Voevodsky, and I associate a triple of objects. So these three functions that I gave over here. So this is kind of one of those real analytic correspondences. This is a Durant current of degree J, and this is J minus 1, and this is an element precisely in the cone, for the definition of a cone of the complex of sheaves. And so now there's some work to show that this map is indeed a map of complexes, and then there's some yoga that you do with the derived category eventually just to have the right setting. But there are some sort of user work of a lot of people. There's a little relation that must satisfy to show that this is a map of complexes, which is far from trivial. But at the end of the day, you show that it's a map of complexes of sheaves, and that's in the level of hypercohomology. That's what induced the regulator map. So let me end the talk with one example, which unfortunately is an example of the complex numbers, but still can chew it. I haven't played with enough so that I can get the real example. I mean, the example of the reals. But I'll introduce a correspondence. So suppose you give a complex numbers satisfying this inequality, define those quantities over here, define a polynomial into variables, and some simple observations you learn in kindergarten. So you put, t is equal to 0, you get that these are the solutions, t is equal to 1, these are the solutions. And for all other t, we have this and that, and some things appear over here. Doesn't matter. But so there's some properties of this polynomial that are pretty simple. And you define a finite correspondence from A1 to this product, gm cross gm, by just the vanishing of that and this equality over here. And so the theorem that if lambda squared is not to the 12th power is not 1, we can find some correspondences that I can add to this that I gave. So this lambda now I put lambda cubed. I just put the cube, the lambda that I had before. These two are called Steinberg correspondences that somehow they are responsible for Steinberg relations in Milnor K-theory from the point of view of Voevodsky's approach to it. So if I add this with something that's trivial, in some sense, I get a cycle. This is a cycle that represents a class. It represents a class in this motivic homology of a point. It's the point. But remember that, I mean, in some ways you can say that Voevodsky got the Fields Medal for saying something about the motivic homology of a point, at least a portion of it. So, Voevodsky much more than that. That's a way of seeing it. And so the question is, well, how do they take the triviality of the non-triviality of that class? So, and this example goes back to, I mean, like, Totaro had an example that are very similar to this, and then others subsequently, but I haven't seen this example using the Voevodsky construction of motivic homology. But the point is that once you make calculations with this, the regulation, so this h1 of a point with coefficient is 2, is just c mod z2. That's what it is. It's the definition, you follow definition and get that. But when you apply this regulator map, so you're just making some integral of some differential form, with a simple path, you get an element of order 24 in this group. It's pi squared over 6, so it has order 24. And so, but then this element is a generator of the torque subgroup of K3 under some characteristic class map from from K3 of complex numbers to this. So that example was there is a similar example by Stefan Müller-Stock and Lewis and Kerr, but they use Bloch higher Chow groups instead, in which case it actually becomes pretty much easier to construct the example than with Voevodsky complexes. So we sweated a lot trying to find the equation for those things. So, and the proof of this I'll just write down. That's because it's interesting to realize that at the end, when you compute the integrals that you need to compute, I'm not writing them. The theta was something. Use this form over here. There's an error right here. But what appears is the Roger logarithm function at the end of the day, and this value is precisely pi squared over 6. So it's an explicit calculation and very simple Euler identity that allows you to identify a trivial element and in the cohomology you might have a later map. So that's it. That's all I have to talk.
Are there any questions?
have this field. What's the option of the way where the organic we are taking inside the complex element?
Well, as I said, this example is used for over C. I did not produce that example in the real case.
What's specific for the way where the argument
Well, I mean, I constructed this regulator in such a way that the same construct applies to the real geometry or to complex algebraic geometry. But in the real case, the recipient is this Deligne homology that picks up a lot of much more subtle aspects of the torsion. And then the hope is that we'll be able to identify more torsion in the regulator map than had been before, because a lot of the time when people deal with real algebraic geometry is that they take the usual regulator, the usual Deligne homology. The idea is to take the invariance under the action of the group, right? But once you do that, you're losing a lot of things. Even in the case of a point, for example, because the Deligne homology of a point, like essentially lives in the column, whatever, n is equal to 1, right? For the complex case, and there's nothing else to the right. Whereas in this case, you still go all the way to infinity with a lot of torsions picked up to the right. And even in the case, if you do with a number field, for example, you can, and so now then go back in history, you can express, for example, when you have the class number formula for a number field, the regulator that appears there is a volume of a certain lattice that comes from the units of your ring of integers in a number field, right? And so that the lattice is actually you can see as the image of, if you use this language, this Deligne homology with coefficients in Z in this real sense, and the change of coefficients when you move from Z to R. And so that map that's what involves the log of the norm, whatever that is. And so in some sense, it's the image of this real Deligne form to the other with Z coefficients into the R coefficients that allow you to calculate the volume of this lattice. So you can interpret this regulator map in the sense that it picks more things as you move farther along. So to the right of the. So in other words, it picks more information than just the usual complex Deligne complex, even for a given point.
Are there any further questions?
When you do real Deligne cohomology, what happens to this wonderful piece of...
Okay, so Pedro and I, as I told you, we have finished this paper, and it's waiting for an introduction for the last many months. And so, in which, for example, we calculate for curves, for example. And so you do have a similar sequence, but
does the Jacobian, the intermediate Jacobian, in some sense appear?
yeah, well, there appears something related to that, but I guess it's a bit more complicated. You want to say something?
The quotient that agrees with the definition of the Jacobian involves the image of the map from Lagrange cohomology to singular cohomology. Instead of just being quotient by imaging the maps, so that by using singular cohomology, it's image from Lagrange cohomology appears.
Yeah.
But it's more complicated.
There are some issues with, I think, differences in volumes of things that you pick up, for example, if you compare with the complex. So they are related somehow. But you see, for example, the H22.
So what kind of group is it? I mean, is it...
A good question. It's, yeah. But for example, in the usual Deligne homology, the H22, right, you can interpret as equivalence class of line, homomorphic line in one of the homomorphic connections, right? That's the usual interpretation. But in this case, there is somehow an obstruction. That's what actually led us to work on this. There is sort of obstruction from this to happen. So the Deligne homology, in this sense, sits between a short exact sequence where you have the Deligne homology on one side And then you have some sort of torsion group, that in the case of curves would be the Brauer group of the curve. And then the kernel of the map is actually the equivalence class of triples, where you have a holomorphic line, you have a line bundle, so we're real in the sense of a theorem that you have with an equivariant connection on it, homomorphic, and a quadratic form that's on it that's parallel with respect to the connections, a triple of things. So actually, years ago, I was visiting Bloch in Chicago, and I mentioned that I thought that this case would have just real line bundles with equivalent connections in some sense, but I was having local obstruction for that to happen, and I tried to explain what the obstruction was. It was something that comes from fixed point set, from the real points. And he said, oh, that's very similar to the problem that Edison was encountering trying to compute the Chow groups of real varieties using descent techniques. So this obstruction appears in the fixed point, that's the real point. So it's a non-trivial extension in that case H2. So those things are, yeah, they have some more interpretations that,
Well, if there are no further questions, then we'll break for lunch. Let me repeat the announcement that tomorrow and Sunday, all of the lectures will be in the Simon Center. And let's thank Paulo one more time.